Word on this computer. All right, cool. So today we're going to be talking about recursion. So yeah, as you can see from the GIF here, or hopefully you guys are all seeing the presentation.
Yep.
Okay, cool. So yeah, as you can see from the GIF here, recursion is basically just repeating a process a bunch of times, but that sounds really similar to a loop. The difference between recursion and looping is looping just repeats the same process, but recursion will actually call the same process every time it runs it. What do I mean by that? So a recursive structure is something that runs itself repeatedly. Or as it says on the slide, a recursive problem is something that can be solved, or a problem that's defined in terms of itself. So a good example of this is something like the factorial function. So this is going back to like your simple grade school math. The factorial of a number is the product of an integer and everything before it, right? So 1 factorial is 1. We forget that 0 exists. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial, 4 times 3 times 2 times 1, etc. So why might this be so going back to what we just talked about for the definition of recursion and the fact that the problem is defined in terms of itself. The factorial problem is something that can kind of be defined recursively, because if you look down here, if I'm looking, let's say I look at the 4 factorial row, right, which is 4 times 3 times 2 times 1. Do you guys see any similarities between how I calculate 4 factorial and, let's say, any of the other factorials above?
Oh, the pattern's the same. You decrement by 1 and then multiply and then decrement again.
Yeah, so it's number one, it's the same pattern. But more than that, let's look at 3 factorial and 4 factorial. What's the difference between 3 factorial and 4 factorial?
One more.
Yeah, so the 4 factorial is basically 4 times 3 factorial in the end of it, right? Because we're sharing this 3 times 2 times 1 bit with this guy, but
Oh, there are answers. So for like 3
yeah,
factorial, the answer is 6. 6 times 4 is 24. And then for 4 factorial, 24 times 5 is 120.
So that would be 5 factorial, but essentially, yes. So we can, 4 factorial, like we're saying, is 4 times, well, the 3 times 2 times 1 thing, but that's the same thing as 3 factorial, which is 6. So if we wanted to calculate the value of 4 factorial, we could say that this is equal to 4 times, now 3 times 2 times 1 is the same thing as 3 factorial, right? But we know that 3 factorial is 3 times 2 times 1. So let's forget about the 4 for a second, and we'll just keep that 4 here. And we know 3 factorial now is 3 times 2 factorial, right? Because again, this 2 times 1 and 2 times 1 is right here. So going back to what we originally said about how recursion is defining a problem based on the problem itself. Sure, you can write the factorial problem as n times n minus 1 times n minus 2 times n minus 3, blah, 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 blah. Or the easy way to write it is this n factorial here is n times n minus 1 factorial, right? Or 4 factorial is 4 times 3 factorial. Now, why does this lend itself to being defined recursively? Well, because in our output, in the thing that we're looking for, which is 4 factorial, we're recalling the factorial function, right? If we treat the exclamation mark as a function, we're saying, all right, the value of 4 factorial is 4 times 3 factorial. And that means that I need to go back to factorial and run factorial for a value of 3. So does that kind of make sense? Any questions about what the factorial function is or why it lends itself to being recursive? Or I guess what recursion is, like in ideal wise. Okay, cool. So it'll be easier once we actually code the example. But for now, let's talk about solving this problem normally. So this is our imperative definition if we want to write it out in more mathematical terms. So again, we've got the factorial of a number is just the number times the number minus 1 times the number minus 2 times blah, 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 times 2 times 1. So this is what we need to output if we write a factorial function. So let me go ahead and switch over to my VS Code. And what I would like us to do is write the factorial function normally. And by normally, I mean basically without using a recursive implementation. And again, so if we can just write it out. So factorial of n equals n times n minus 1 times n minus 2 times blah, 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 times 1. So where do I start? So before we jump into writing the function itself, why don't we start thinking about what the function is, what our inputs and outputs are, and start pseudocoding. This is a step that I usually like to take. So I like to make a list of inputs and a list of outputs. So what do I take into this function for the factorial?
Value.
Okay. So let's give that value n, and we can just say value to be factorial. That is totally a word. And what about our output? So what do we need to output?
The factorial.
Yeah. So we can just say factorial n. We'll just say factorial of n. How do I get from this input to my output?
You're gonna break down the n into elements.
What do you mean by that, Ivan?
So maybe 4 needs to be broken out into a 3, a 2, a 1. So it needs to be in a loop somehow, broken down.
Okay, cool. So we have a loop. What type of loop do we want to use? Do you think a for loop would be better or a while loop?
While loop. While it's greater than 0.
Okay, so we could have like a while, and then we probably need a counter variable, right? So we could have, well, first we need to initialize a counter. So what do we want to initialize our counter to?
What do you mean initialize our counter to?
So we need to set a variable for our counter before we run it in a loop, right? Because we can't just say like while counter and then set some conditions for it. We need to first give it a starting value and then after that write our condition.
We just make counter n, or
Yes, for multiplication is 1. If it's addition, 0, I believe.
Yes.
And since you multiply to each other, you have to multiply to 1. Starting 1.
We could do counter equals 1, but I think for this implementation, it might be better to go with what Grace was saying for counter equals n, and then after that, we could do while counter is greater than or equal to 1. And Michael, right now, the answer for that is no. In 20 minutes, the answer for that will be yes, but we will see why. So Good that you're already thinking about it, though. So, okay, so going back to our normal boring example. Why would we have a counter? Jonathan, that's because we're not doing recursive implementation just yet. We're just doing a normal loop one, just so we can talk about just so that you guys can understand how the factorial function works before we jump into recursive implementation. But also, a lot of the time, you don't start writing a function recursively, like when actually programming. Usually, what you'll do is write your code out using loops, and then at some point later realize, oh, this would be way shorter if I did it recursively, and then rewrite it recursively, and then see how much time you've saved, which is essentially what we're going to do here. So while our counter, so what do we want to do while our counter is greater than or equal to 1? So obviously, if I run this code right now, or ran this pseudocode, it would just run infinitely. So I need to do something inside my while loop.
Store it.
Store what and how?
You need to increment towards the base case.
Okay, so that could be like counter minus equals 1. What else?
The result equals like n times like something.
Okay, cool. So if I just wrote that down, let's say calling our result factorial n, and you're saying that that's going to be, so sorry a second, what did you say the formula was that you wanted to use?
Like something like n equals like n right now at this loop is n. Next time like n equals like that result equals n times n minus 1, just like this loop like that. That's what I'm.
Okay, gotcha. So yeah, that's what we're using. So the n here is basically going to be our counter slash factorial, right? So here, let's delete this for now. So let's say that I run this function with, let's say that I have n equals 4. So now counter is going to start at 4, then it's going to go to 3, then it'll go to 2, and then it'll go to 1. So how can I turn this list of things in my counter into an output? Let's see what folks are saying in the chat. So appended counter and make an aggregator. Oh, go ahead.
You could create another variable and set it equal to 1, and then every time you loop through, you multiply that variable's value by the counter.
Perfect. Yes. So factorial n times equals counter. Okay. And then at the end of this, all we need to do is like return factorial n. So does the intuition behind what Michael Lake said make sense to everyone, or is anybody confused about why we would need to multiply our storage variable by counter and then decrement counter for each iteration of the loop? Okay, Ethan, you say we might not need a counter. Why is that?
So if this is a function and they're putting in a number, you could just subtract the number until it's until it's 1.
Yeah, we could do that. Honestly, though, I personally like keeping counters in because it keeps the implementation a little bit cleaner. And also some languages have a problem where if you input a number into your function argument, then changing it within the body of the function can sometimes change the original variable too, which isn't great. Also, if you put in Actually, no, I was just saying the same thing. Yeah, but yeah, that's the main reason why I like using counters instead, and also just because counters are more generalizable. But you're right. We could say, well, n is greater than or equal to 1. Factorial n times equals n minus equals 1. That would work in this specific instance as well. But just as a personal preference and something I recommend for you guys is using like an additional counter variable isn't always a bad thing.
A little bit of redundancy is good, or a little bit of supposed redundancy is good.
Yeah, basically. So now we can define our actual function. And again, we wrote this out as pseudocode, turn it into actual code, right? So we've defined our factorial function. It initializes a counter at our input value, and it creates a dummy variable for our output. Then we create a loop that checks whether our counter is greater than or equal to our base case of 1. It'll multiply our dummy variable by the counter and then increment or decrement the counter by 1. And then it'll keep doing that until our counter reaches our base case. And then after that, it just returns the result. So don't just trust me that this works. Let's also confirm that. So we could print, let's say, factorial of, let's start off with our base case of 1. So if we run this, where's the run button? And factorial of 1 is 1. That's great. Factorial of 2 gives us 2. Factorial of 3 should give us 6. Factorial of 4 gives us 24. Okay, well, I said that too fast, but that gives us 24. And we can keep on going like this. We can also do factorial 0, as Robert said, and that also gives us 1. So this factorial function that we wrote out works. Does anybody have questions about why this normally implemented factorial function works correctly? I'm going to zoom now. So now, going to do the recursive version. Before that, we switch back to the slides real quick. So again, going back to our definition, right? This formula is basically what we just implemented with our while loop. Right, we're decrementing our counter every time, and we're just multiplying them all together and smushing them in, and then returning them. And you can see here, this is the imperative solution, or I guess I like to say normal solution because it's non-recursive, right? Theirs is a little bit shorter, but they're creating a dummy variable for the result. And instead of using a while loop, they're using a for loop over a range, which is another acceptable way of doing the same thing, and multiplying by I, and then returning the result. So same thing, just a for loop instead of a while, and a tiny little bit short. But yeah, both of the approaches that we just used do not use recursive. So let's move on to the recursive part. So this goes back to something that was said earlier in chat by, I think it was Michael Lake, talking about how we can recursively define the factorial function. So again, if we go back to the bottom part here, remember, so the 4 factorial is 4 times 3 times 2 times 1. Where do we see 3 times 2 times 1? Oh, wait, that's right up here. So, and what is that originally? That's 3 factorial. We can drop that right in here. And yeah, this is equal to 4 times 3 factorial. Now, in 3 factorial, it's 3 times 2 factorial, and 2 is 2 times 1 factorial. And we can generalize this approach to say that for any number n factorial is n times n minus 1 factorial. So now we can go back to our recursive implementation. So if we go back down here, remember that So n factorial equals n times n minus 1 factorial. Let's define a new function. Say this is factorial recursive, and we'll take in n. So how can I turn this statement into a function?
First step is to establish the base case.
All right, cool. Establish base case. What is our base case?
When
1.
it gets down to 1. Yeah.
Okay, so n equals 1. So we can say if n equals 1, and what do we return?
Return 1.
Okay, double equals. Now, what if n isn't 1? What do I want to return?
Ethan wrote it in chat.
Oh, thank you. All right. This is basically your else. We can return n times our recursive factorial of n minus 1. So why does this work? So going back to, so again, let's pretend that we're inputting n equals 4, right? Just like we did in our example up here. So oh, Ethan, good catch. Yeah, we could do n equals 0 as well, because 0 factorial is 1, so that works too. And we could also just do 1 just for kicks, just as if n is less than or equal to 0. Let's say somebody puts in a negative number, we could just print factorial only takes positive numbers for our purposes right now, and then just like return none. No, let's do less than 0. There we go. So Grace, that's a good question. So the reason that we will start off with n equals 0 is because 0 factorial equals 1. So it makes more sense to have 0 as the base case instead of 1. Because if 0 factorial is 1, then 1 factorial is 1 times 0 factorial, which is 1 times 1. Grace, that is a good question. That is called a secret of mathematics. That's basically just how mathematicians define the factorial function, is to start at 0 equals 1. Why? Not sure, but I'm sure that there's more resources out there about this if you really want to go in deep dive. But for now, just accept it as a fact of life and the universe as defined by mathematicians.
So normally when
So-
using multiplication, oh, sorry.
Oh, good.
Normally when using, I don't know when else you would use like recursion with multiplication, but is that a specific case for factorials, like that you would want to start with 0? Like any other case, you'd probably not want to use 0, correct? So you don't end up with 0 using multiplication.
Um,
I don't know if I'd asked that quite correctly, but
I mean, so the base case is going to be different depending on what your function is, and what your implementation is. So while we might be using 0 in this specific example of the factorial function, another program that we write recursively might not use 0 as its base case, if that's what you're asking.
yeah, I was just curious if that was a case specific to factorial, since that's kind of a weird situation how 0 factorial equals 1, when normally in multiplication anything times 0 is 0.
Okay, I see your question now. Yeah, so in that case, you could say that the base case of 0 is kind of only for the factorial function. But just in general, the way that we want to think about base cases isn't like, oh, this base case can be generalized to any function. This base case can be only applied to this function. The best way to think about a base case is what what are special conditions for my function? In this case, for this implementation of factorial, our special condition is n equals 0. For another function, it might be n equals like 15 because you need to stop at 15 or something like that. So that's the way that I would encourage you to think about base cases, instead of as just being stops for a function. You want to think about it as when do I have weird things that regular function behavior cannot account for?
Okay, makes sense. Thank you.
Yep.
So there's instances where you
So-
could have multiple base cases.
Yes, very much so. And we have multiple base cases right here. So we have one of our base cases. Let me just do n is negative or 0. So one of our base cases is if n is less than 0, right? Because you can't get a negative factorial. So in that case, I'm printing out this little string telling people not to put in negative numbers, and I'm returning a value of none. Similarly, my next base case is n equal to 0? And if so, I'm just returning 1. So you can sandwich base cases on top of each other for as long as you need. But generally, you only really want to have a couple of base cases. Otherwise, it gets too long and cumbersome. So like I wouldn't set a hard number limit to it, but if you find yourself including multiple if statements one after the other, you might want to think about restructuring how you're coding. But to answer your question, you can have multiple base cases. Oftentimes it's good to, because it's really easy to have a runaway factor or runaway recursive function. And base cases stop that from happening. Any other questions about the recursive implementation of the factorial function that we just came? Yeah, to recap, what we're doing here is we're doing for n equals 4, right? This is going to be 4 times 3 factorial, which is going to be 4 times 3 times 2 factorial, which is 4 times 3 times 2 times 1 factorial. And I'm just going to copy paste now because I do not want to keep handwriting this. And then the 1 factorial bit is just 1 times 0 factorial. And then we can just start evaluating this from the inside out, right? So 1 times 0 factorial is 1, 2 times 1 is 2, 3 times 2 is 6, and 4 times 6 is 24. And then that's the final answer that we get. And Grace, that is terribly perfect. So, and again, we can test our recursive function if we want to as well. We can run it. I don't think we need to right now. If you guys want me to call the function, I can. Would you like me to call the function?
Why not?
Yeah, okay. Here, let's do 4 again, just to make sure, because that's a nice base case, because it's small and easy to hand calculate. So we'll wait for this to run. Oh, that's still from our old factorial. Let's do 4 there too. And just make sure both of them, yeah, they both give us 24, which is okay, that's great. Now the other thing that we can do is here, let me switch screens and go back to your slideshow. So this is, and again, the same implementation of the factorial function. Basically what we wrote, we just added another base case and used 0 instead of 1. But going back to the imperative solution on the slide, this thing takes up 1, 2, 3, 4, 5 lines of code. Our factorial function here takes up 1, 2, 3, 4. That's a difference of 1 line, which isn't very significant, but for larger, more complicated recursive functions, you can easily save like half of a program by changing it to a recursive implementation instead of non-recursive. So it saves you time, and it saves you programming space. And it also just looks a lot cleaner too. Yeah, Fibonacci sequence, like you're saying, Ethan, is a perfect example of this. So if we want to compare our two solutions, the iterative function that we wrote is step by step, right? We're using a loop. We're going 1, 2, or like 4, 3, 2, 1, and smushing them together. And we're using conditions. And our variables, like a result variable, help us build our solution up as we go. But for a recursive solution, we're using a recursive case in order to build this up. And our base case signals the end of the recursion, which is our one conditional at the start. And instead of using variables to build up the recursion, like we did here with result, we're using return to bundle it up and return it to the caller in the call stack. Which is faster in space-time complexity? Ooh, good questions. Okay, so we're going to talk about big O notation and time complexity tomorrow. So Jake, I would encourage you to hold on to that. Which is faster? Michael, that's a good question. It depends on how you think about speed, I suppose. So in terms of runtime, we could test that. If you wanted to test that, you'd need to import the timing library and check how, like, the number of milliseconds it took to run each function, which is something that we're going to do. That's something that we should be doing tomorrow. And we're talking about big O notation. The first iterative function runs in, I believe it's O of n, because as n gets bigger, the number of times you run this, or the number of times the loop runs, scales upwards with n. Versus the recursive function, I believe should run in O of log n, but I'm not sure. You might want to look this up. But for anybody who has no clue what I'm talking about, you will find out in approximately 24 hours.
We definitely talk a little bit about log n today. In terms of complexity analysis for recursive stuff, it's usually exactly the same, because calling the function is no different than if you just did it iteratively, in the body of the one function. But recursive stuff tends to be, on average, less efficient because you are calling a function that calls a function that calls a function. And Umar is going to get into that in a bit when we talk about the call stack. Back to Umar.
Thank you for that explanation, Benjamin. I think actually I was confusing the log n stuff with the stuff we were doing for today. So thank you for that catch. But yeah, so and we can also look at this in more detail if we talk about the call stack, which I believe should be coming up in 2 or 3 slides. So we go back to how recursion works. We in our code we have 3 steps, right? So the step we have got the base case, which is if n equals 1, then return 1. Then we have a recursive step, which is the factorial of n minus 1, right? Which is calling the function again. And then our return case, which is just the return n times factorial minus 1. So again, the 3 steps. Given a factorial n, you're going to do some stuff and then move on to the next recursive case, right? So when we have factorial 5, the doing stuff is 5 times. And then the next recursive step is factorial of 4. The base case is our special case where we need to stop running the function. Because if we keep running it, it's going to go on for until n is negative a very giant value, which isn't what we want. So we need to have a base case to stop that recursive function from running away. And for those guys, it was n equals 1. For the code that we wrote, it was n equals 0. And then lastly, we have our return step, which is, in our case, basically where we return In this case, they write as 5 times factorial 4, or where we return n times factorial of n minus 1. So this is all well and great, and we can see that this actually returns something. But to understand how recursion works in practice, we're now going to talk about something called the call stack. So the call stack is basically an order in which your computer runs functions that have been called. So in the example below, we have 2 functions. We've got a greeter string function and a greeter function. And then we call the greeter function with an input of Ben. So this example seems really simple, but it's good to illustrate how the call stack works. So as it says at the bottom, the computer runs this code line by line. So what does the first line do? The first line says, I want to define a function. What's the function called? Greeter string. What does the function take as an input? Name. So your computer's like, okay, cool. I know I now have a function. It's called greeter string. Let me keep that in the back of my head. And now it's going to define greeter string using this return function. It's like, okay, cool. I'm not calling any functions, so I'm going to keep that in the back of my head. It'll do the exact same thing when it defines the greeter function, when that takes in a name too. And now we move on to line 7, which is where we call the greeter function, right? So this line here refers back to this greeter function, with Ben being our property of name. So when we call a function that function call gets added to the appropriately named call stack, which we can see on the right. So it gets added to that bottom of that call stack. Now, when we run greeter Ben, what are we actually running? Like, sure, we're running the greeter function, but in reality, what we're running is print greeter string name, where in name is value of Ben. Let me clear this. And so, as it says here, in order to evaluate greeter Ben, we need to evaluate the body of the greeter function. And in order to evaluate that body, which is print greeter string name, we need to evaluate greeter string name. And then that, again, because that's calling this function, that is also added to our call stack. And why is my mouse being weird? There we go. Okay, so I'm just going to stop on this slide for 1 second and then go back to the next one. So if we now run greeter string Ben, which is this top guy, that just returns an F string. Does returning the F string call any other functions? It doesn't, right? So because it doesn't call any more functions, and we're just returning something, we're done using the call stack. Kind of. So as it says here, greeter string Ben evaluates to something, right? It evaluates to that F string, hello Ben, and it returns that F string. So because that function doesn't call any other functions, we don't need to keep adding to the call stack. So we can pop that off of the call stack. And here, let me write this. So we essentially replaced our, why can I not, there we go. We have essentially replaced our greeter string Ben call with the F string hello Ben, like that. And now that is going to get, now that return value is going to get passed in to the call site. Now, what is the call site? The call site is this greeter string name thing. So what's the greeter function going to do? So we can now cross out greeter string name, replace it with hello Ben. And what's greeter now, or what's our function going to do? It's going to print out hello Ben. And then by doing that is printing out hello Ben, calling a function. Sure, you could say it's calling the print function. That can pop it onto the stack. But what's that essentially doing? that's just putting something out to the console. It's not calling another defined function like this. So eventually, as it says in the slide, it'll evaluate print hello Ben. It prints to the console. We don't call any other functions after that. So we can pop the greeter Ben function off the call stack, and we don't return anything. So we're done. So to recap, defining functions doesn't add to the call stack. Running a function, calling a function, adds it to your call stack. The more functions you run on top of each other that call each other, the bigger your call stack gets. And your call stack evaluates by basically going from the top all the way down. So, any questions about how the call stack works?
Yeah, why would you do this?
This isn't something that we do. This is something that computers do on their own. Why they do it? I'm not particularly sure. I think that's just the way that computers were developed, but I think Benjamin knows.
Yeah, so like Umar said, it's not you doing this. This is happening behind the scenes. But it's one of the reasons that different data structures are like, even if you never make them yourself, they're really built in at this point. So this is done because if you try and call greeter Ben, that can't finish until it runs the body of greeter. And in the body of greeter, that can't finish until it runs greeter underscore string. And once you run that, that runs something. And then it can like, you know, so like sort of it grows up and then it collapses downward. But if you didn't, like, this is the only way you can sort of maintain the fact that you're in the middle of some work and you have to do something first, but before that you have to do something else. Before that you have to do something else. And so that's why you do it. Because otherwise everything would have to be at the top level, as opposed to you can call something, which calls something, which calls something, and they always know where to return. And obviously in a real call stack, there's a little more information there. Like it has to know like where it's returning to in terms of the call site. But the general structure is about like, you know, you can't finish something until you do something else, and you grow that until you hit what's essentially a base case, which is something that, you know, evaluates without having to call anything else, and then the whole thing collapses.
Does it look at all languages the same way in the same order, the call stack?
Yeah, more or less. As in, this idea of a call stack is super common. It's going to be in almost any language. I see some people in the chat mentioning heaps. Like, I don't really remember that concept too well, but if you are like a C programmer, you know about this thing called the heap, because it's another data structure that, you know, is the actual way like you're allocating memory. When it comes to, sorry, can you repeat your question? I'm realizing I got a little off.
Sorry, I was just saying, does the call stack look at all languages the same way as far as evaluating the order of which it's I guess doing
I would say more or less, but it's a good question because this idea of the call stack assumes like things happen in order. And much later, when we're in React Week and we get into JavaScript more deeply, we see that the call stack exists, but there's also this thing in JavaScript called the event loop. And that's what handles the whole like, oh, you did something asynchronous. Well, when does that happen? But it gets kind of confusing. Most languages like Python, which are purely synchronous, it happens like this, exactly. Okay, back to Umar. Yeah, the event loop is a funny name. Yeah, that would be a good title, the event loop. Cool. Back to Umar.
Yeah, so also just to answer Grace's question in chat really quickly. As Bennett said, the stack is generally pretty big. So running out of space, unless you're doing something terribly wrong, which is what we're going to do in like 30 seconds, you should be fine to run recursion as long as you stop it. Do not let your recursion run away with you. Otherwise, you get problems. It's sort of like an infinite while loop. Same principle. But The main thing to keep in mind is we're just talking about how the call stack works, because this is a concept that you're going to see regularly, one. And number two, it's also just good to understand it for if you have, like, especially when you're talking about things like recursive functions, it's good to see how your program evaluates itself and how it runs through things. So in other languages, like C, for example, or other editors, you can step through your code line by line to understand exactly what each step is evaluating to. And the call stack is essentially gives us the same measure of doing that. And if you, again, there's no need to apologize for asking questions. If you guys have questions, ask them. Simple as that. And yeah, let's see if I missed anything in chat. Don't think so. But yeah, Benjamin, thank you for the assist. And all right, so we talked about this, talked about that, talked about this. So real quick, let's talk about how the call stack works for recursion. And we're going to do this using the factorial 5 example. So okay, forget the execution part. That's going too far. So let's start off with line 1, right? So when we're evaluating everything, we're going to start off by defining the factorial function. What is the factorial function? All of this stuff inside of the DEF factorial n piece. Great. Now we can move on to evaluation. So the first thing we do is we evaluate factorial 5. We pop it on to our call stack. Now, what is factorial 5? In fact, by running factorial 5, we check is n equal to 1? No. So we run n, or 5, times, what's this? We're running factorial of n minus 1, or factorial 4. Factorial 4 is a function call. Function calls get added to your call stack. So this guy gets lopped onto here, as shown in the graphic on the right. Now we have to evaluate factorial 4. Evaluate factorial 4. Is 4 equal to 1? No. So we return 3 times the factorial of 4 minus 1, which is 3. Factorial of 3 minus 1, which is 2. And then we just keep doing that all the way to factorial 1. Right? Like so. And now factorial 1, which is our base case in this specific example, factorial 1 equals 1. So this thing is going to collapse out of the call stack to 1. And let me pause this. So yeah, as it says, we pop the factorial 1 stack frame and we return 1 to our call site. What is our call site? Our call site is going to be this right here. So remember, the return n times factorial n minus 1 line. This guy is going to replace this whole expression when we run factorial 2. So when we do that, all the statements now collapse, just like what we talked about when I was demonstrating in VS Code and I was collapsing all the parentheses. That's kind of the equivalent of the call stack, right? So here we got 2 times 1, which is 2. And now that 2 gets substituted in for the factorial of 2. Do remember the factorial of 3 is going to be 3 times 2 factorial. Now this guy gets plugged in for the 2 factorial. And then we got 3 times 2 is 6. And remember, 6 is 3 factorial, and 4 factorial equals 4 times 3 factorial. So that's going to collapse our 4 factorial. And then 5 factorial gets collapsed the same way. And then, so 5 times 24 is 120. This 120 is going to be replacing the whole return expression. So we return 120. And as you can see here, there's nothing left on the call stack. So the original call site, what's the original call site? Original call site is this guy. It's going to return your your return value of 120. And then after that, there's nothing left.
Frozen. I think your
Oh,
screen
whoops.
froze.
Okay, is it unfrozen?
There we go.
Okay, cool. I think I accidentally paused it. Thank you. Okay, so where did it freeze up? Okay, wait. Why is it's not working? Okay, there we go. Did it freeze up here or like before?
Like
It
when you
froze up
when you
the
started to
one.
collapse, when you started to collapse your call stack, it froze.
Oh, okay. Gotcha. Thank you. All right, so okay. So back to collapsing the call stack. So remember factorial 1 here is going to be our base case. So factorial of 1 is n equal to 1, returns 1. So this entire thing collapses into a 1. And we'll see that. Okay, come on, stop. Work. There we go. On this slide, the 1 collapses. And then our 1 now becomes factored into the factorial 2 function, right? Remember the 2 factorial 2 is going to be 2 times, how do I write a 1? 1 factorial. What is 1 factorial? 1 factorial is just 1. So this guy goes here. So 2 times 1 is going to just collapse the whole thing in there to 2. And we'll see that on the next slide. Yep, 2 times 1 is 2, which is exactly what we like to see. And now remember that 3 factorial is going to be 3 times 2 factorial. Now what's 2 factorial? 2 factorial is 2. So this guy goes right back in there. So now we get 3 times 2, which is going to be 6. And then the 3 factorial, and then that collapses into the 4 factorial. Just remember 4 factorial is 4 times 3 factorial. Now this guy is 6, so it's 4 times 6, which is 24. And then we do the same thing for 5 factorial. The 5 times 4 factorial, we know 4 factorial is 24. So we do 5 times 24, which is 120. And we don't have anything else at the bottom of our call stack. So we return 120. And where's the 2? There we go. So the 120 here is going to be this entire thing. Now this entire thing is the last thing that gets returned. And that basically drops into our factorial 5 function, which now completely collapses our call stack. And so the end value that we get out is the last thing that we returned, which is 120, which was the thing at the bottom of our call stack. And now at the end of this, our function terminates because there's no other function calls, so we're done. Does the call stack for factorial make sense? Or the call stack, I guess, in general, make sense? Does anybody have questions about that? Okay, I'm going to zoom now. So we have basically one more slide to go, and then we'll take a 10-minute break. But I want to go back to Grace's original question about why the call stack is so important. Let's pretend that we wrote a factorial function that did not have our base case. So we forgot about the if n equals 1 or n is 0, return 1. Let's just say our factorial function just ran the n times the factorial of n minus 1, and it ran that forever. So why is this bad? So let's say using this function that I want to calculate, let's say I wanted to calculate my good old 4 factorial of that. Well, this is going to equal, now it's 4 times 3 factorial. But what's 3 factorial? 3 factorial is going to be 3 times 2 factorial. But what's 2 factorial? It's going to be 2 times 1 factorial. And I'm going to go over here because I'm running out of space. What's 1 factorial? 1 factorial is going to be 1 times 0 factorial. Do I ever have a stop at 0? No, that's kind of weird. So now we can put 0 back in. So 0 factorial is going to be 0 times negative 1 factorial. And then negative 1 factorial is going to be negative 1 times negative 2 factorial. And oh my God, this is going to keep going forever until we hit the integer limit or until our call stack gets exceeded. Why? Well, we never told factorial when to stop. It's the same thing as when you have a while loop that you just never reach the condition for. It's just going to keep running and running and running and running and running and cause you a big memory problem. For our call stack, we get the exact same problem. It'll keep running and running and running until, now remember, the call stack is full of uncalled function calls. So if we go back here, right to our factorial, let me clear this. All of the everything in your call stack are functions that have been called, but that haven't been collapsed just yet, right? We haven't returned any values. So by running our factorial function without a base case, we go 4 times 3 times 2 times 1 times 0 times -1 times -2 times -3 times -4 times ad nauseum. We haven't evaluated anything. We've just added on to our call stack. So if you imagine, a nice way that I like to think of the call stack is like you're making like a giant stack of pancakes and you're just adding on to that stack of pancakes. And then when you evaluate the functions in your call stack, it's kind of like eating a pancake. And the goal is to reach like an empty plate. It's a weird analogy, but if you're a food person, it might work. So as you're collapsing your functions, as you're running them and as they're returning things, you're eating your pancakes, so your call stack diminishes, which is great. But if you keep on adding pancakes to your call stack, like again, factorial 1, forget the base case. You're going to add factorial 0, factorial -1, factorial -2, and we just keep going up. You're going to get a never-ending tower of pancakes, which is eventually going to collapse or explode. In this case, we have the pancakes will explode, and that's what happens when you get a stack overflow. So this is why base cases are really important. But yes, Chris, go ahead.
This is somewhat, I guess, a side question. Where exactly does the call stack live? Like, is that inside of our editor or like is that inside of RAM? Like,
That's a good question. I'm not actually sure. Benjamin, do you know?
Sorry, do you ask the question again?
yes, I was just curious as where does the call stack live? Is it like inside of our program or is it inside of like RAM? Like, where exactly?
I mean, it all lives in memory ultimately. The call stack is likely created and destroyed when your program runs. So the call stack is like when you run Python, factorial.py, that Python program is what's building the call stack.
Thanks.
Yeah, and I think that way you could have like theoretically the multi-core, you could have 2 programs running at once. They're using separate call stacks. And Ethan is asking if there's any way to access the call stack and manually change position of calls within it. No, not as far as I know. That's where you want, like where they draw that distinction, where even if you were using C, they're not going to give you that level of access because maybe you could do something interesting and efficient with it. More than likely, you're going to shoot yourself in the foot in such a way that it's just catastrophic. So you don't have access to that sort of thing. Yeah.
And adding on to what Benjamin was saying, you generally do not want to play with the call stack just because that's default computer behavior. And messing with the call stack might not let things work very well. So generally that's something that I'm fairly sure there's got to be a way to access it somehow, but it's definitely not a regular, normal, easy way to access, like compared to other things in memory. So would not recommend trying to do that. But you're welcome to look into it on your own if you'd like to. And if you find a way to access it or change it within computer memory, let us know because I'd actually be interested to hear about that. Jesse, to answer your question, C and its derivatives. So you've got C, C++, and C#. The C# is used a lot in video games. So if any of you guys have played anything based in Unity or the Unreal Engine, all of the mechanics in those games are all coded well, mostly coded in C sharp. C and C++ are often used to create like software packages for other languages. And they're also on occasion used for data analysis. You'll also see them being used for things like robotics. So they have different uses than some other languages like Python, but there's a lot of crossover for between.
Yeah, at this point in history, I mean, it used to be everything was C, and C++ is basically just C with all the cool features you get in Java and more advanced languages, but like no, what they call zero cost abstraction. So you're not paying for it in terms of efficiency, but C is mostly for video games at this point and other high performance things where high performance is necessary. And the reason is because you don't really notice it when you run your program, but the fact that you're not allocating memory and then deallocating memory, that's because it happens behind the scenes with what's called a garbage collector. And so like every minute or so, or 2 minutes, your program is maybe devoting like, 5 seconds where it slows down by like 30% because it's focused at, it's doing this other thing that is more important for the moment, which is the garbage collection. You don't notice that in most programs. Video games are an example of something where you want it to run, you want it to be rendering a new frame 60 times per second. If there's any slowdown because you're doing this garbage collection thing, people will notice and it looks bad. And so video games are one of those few things where you just cannot have any lag at all. By the same token, I'm sure like if someone was making like, those like surgery robots that exist, they cannot have any lag in those. So they got to do it in C because they don't like, it's not worth the trade-off where you don't have to think about it, but you do get this tiny bit of slowdown. For the great majority of applications, that's not your concern, especially with web-based stuff. Web-based stuff, your slowdown is going to be because you're talking to some server and it's halfway across the world. That's going to take like 3 seconds to happen. You're not too worried about these tiny little losses in speed because your language is doing some garbage collection. Cool. Back to Umar.
Yeah, thank you for that explanation, Benjamin. But yeah, so again, C and its derivatives all focus really heavily on memory optimization and just making the most efficient use of it. While Python and Java and other languages do too, but C is kind of like the OG of sorts that really, really gives you a lot of control over memory stuff, which is super important for hot and really intensive applications like video games or things that have a lot of stuff going on in the background that you need really low latency for.
Yeah, and notably, if you want to build it, like Python, is this higher level language, but if you want, and you don't have to worry about memory allocation, but if someone wants to build a Python compiler, they have to do that in C. At the end of the day, you always have to work in C. You might be asking, well, what's the C compiler written in? C. It's kind of nuts. But basically, you have to get that load of the hardware to do certain things. But for the most part, most people don't want to have to think about that because it's so easy to shoot yourself in the foot. Back to you, Mark.
And to go back to something that Roger said in chat, learning C++/C# for game dev is actually super rewarding. It's something I spent like a summer doing like a little while ago, just like playing around with Unity and Unreal Engine. And it's once you learn the basic concepts through a language like Python, the basics are pretty easy to transfer over. It's when you get into like the weeds of things that it starts getting more complicated, but it's the same way with any language in any application.
I also feel like having something fun and interesting like a video game or making a video game to apply that knowledge you're learning to, as opposed to just contrived problems like solve this. Johnny has 5 apples. Like, yeah, okay, whatever. I feel like that helps a lot more with learning something.
It definitely does. But don't worry, we're not going to be making video games in Platoon exactly, but that's where give it, Benjamin, I would say what, like 4 weeks or so before we start getting into the actual fun projects that'll really help you guys learn. So I'm sure that you guys have heard of this spiel before, but you've got your personal and group projects. But before that, once we start getting into the more complicated web-related parts of our curriculum, you guys are going to be building actual functional websites that do stuff, like collecting news or creating like a social media sign-up page and stuff like that. So those less contrived, more fun / imaginative examples will definitely be coming up soon.
Yeah, when we get to more, by the time you're done with the whole web development stuff and you're doing the personal and group projects, you'll very much be able to do practical stuff. And you're right, that like that helps you learn in a very different way. It's kind of impossible to, like, it would be so cool if you could teach this stuff while making a video game or something, but it's hard to really see how complex this stuff really is, which is why you're doing contrived problems. I remember in college, it was a joke that the computer science students would like sit in the library and they'd be looking at a blank screen for like 6 hours, and then suddenly like a white dot would pop on and they're like, oh my God, I made progress in my, computer graphics class. It really was that, like, just to like do the very, very basics is surprisingly difficult. So these contrived problems, even though they don't, it's like, what is this? Why does this matter? It's just kind of proof that to do anything useful with computers, you need to build up layers and layers and layers. Back to you, Mark.
Yeah, so I think that's about it for the first part of morning lecture. Does anybody have other questions or comments before we take a 10-minute break? Okay, cool. So again, just to recap what we talked about before we take our break, we spent way too long talking about recursion. So remember that recursion is something that calls itself repeatedly, right? And we use a factorial function to determine how to do that. So with our function for factorial, again, we have your recursive function has 3 parts. You've got your base case, which is where you stop, a recursive step, which is where you do it over again, and then your return, which is where you do your output. And please keep in mind that the call stack is a thing. And it's just like, again, a tower of pancakes is the easy way to think about it. You put more pancakes on as you call more things. And then as you evaluate those things, you eat the pancakes and they drop off. And just try not to overflow your stack, and make sure to keep your base cases in. And yeah, that's about it for morning lecture. So let's come back together at, let's make it 10:25. In the recording. So we talked a little bit about what recursion is and how it works. But as some folks mentioned, the play examples that we used are honestly kind of boring and not all that helpful for real world applications. So what is a real world application of recursion? Well, binary trees are a really good one. So trees are an advanced data structure that you'll see used quite frequently in data analysis. A tree is basically a collection of nodes that are all linked together somehow. In this instance, they're talking about trees that grow downwards. So like you see here, you've got your the root node of 56, and that's got a head and a tail. I think the head here is 22 or 81, and the tail is the other one. And then each node going from that also has a head and a tail. Sometimes you'll see trees drawn from like this top to bottom approach. Sometimes you'll see them drawn the other way. So sometimes you'll see them drawn like this. Other times, sometimes the way I like to draw trees is like side to side. So you also see them drawn like so. But they're all basically showing the exact same thing, just in different pictorial representations. There are other types of trees. So binary trees, like the ones here, have a central node, and they've got a head, and they have a tail. So it's sort of like the linked list, but not. There are other types of trees, though, that have more than 2 branches. You could have trees that have 3 or 4 branches. You could also have trees that collapse back in on themselves eventually. So you could have a tree structure that looks sort of like this, where and all the branches come back to one node as well. But for today, we're just going to stick to the simple-ish case of binary trees. Chris, go.
Sorry, just a stupid question. Do we have to traverse these the same way we do linked memory? Like, does they only go in one direction?
So that's a good question, and this is actually a good slide to talk about that. So for your linked lists, you can only really traverse them back or forth, right? So here, I'm just drawing out a example linked list. The only way that we can either traverse a linked list backwards or forwards. So it can only go this way. But we can think of a linked list as basically being like 1D of sorts. Like think about a linked list like you're moving across the line. You can only move across the line forward or backwards. But with a tree, we can navigate a little bit more interestingly. Okay, actually, let me undo that. So for a linked list, your tail node has to be the same as the head node of another entity in your linked list. But for your tree here, I mean, for example, this 30 node, it's not associated directly to any of these other nodes except the 22, right? So it might have like the left node, for example, could be, or actually 30 doesn't have any child nodes. It doesn't have any branches going from it. We can't do that in a linked list because in a linked list, what that would look like is basically have something over here. It doesn't work. So in terms of traversal, yeah, for a linked list, whereas we go from left to right, in a tree, we kind of go up and down. And we'll see more about how this works soon. But basically, if you're going down a tree, you'll start at your root node and then either go like right or left. And then depending on if you go right or left, then you either go right again or left again. And in going right and left, you also automatically go down. So it's a bit more confusing than a linked list, but sometimes it's a little bit easier to understand as well. So going back to what you were saying, and also, Chris, did that answer your question?
Yes, it did. Thanks.
Yep. So going back to what you were just talking about with linked lists. So there's similarities between linked lists and trees. So both of them have a node structure. But whereas a linked list has the head always linking to a tail, a binary tree does not always have that as the case. So in a binary tree, you either have a leaf node or a branch node. So leaf nodes are basically like places where your binary tree ends. So like the 10, the 30, the 77, the 92, they stop there. And a branch node is a node that has one or more subtrees. So example, let's analyze the 22 node. So the 22 is going to be a branch. Why is it a branch? Because it's got, well, the 10 is attached to it and the 30 is attached to it. So those two nodes are directly attached to it. So that makes it a branch. Now, what are the subtrees of the 22 node? Well, the left subtree is going to be 10. And the right subtree is going to be 30. Do the same thing. Here for 56 is going to be our root. Then we have the left subtree. And then we have the right subtree. And this left and right subtree thing is something that we're going to be using quite frequently for quite extensively for about the next 30 minutes or so. And there's also notation that's used for trees throughout programming. Okay, so here's an implementation of a binary tree. I'm going to feel free to put this into your VS Code because I'm going to do that momentarily as well, because I want us to compare and contrast binary trees with linked lists. So let me go ahead and go to Python. Okay, so this is the recursion demo. I'm going to comment all of that out for now, and we'll start here with binary trees versus linked. Right here, let's do the linked lists versus binary trees. Alrighty, so let's start off with a linked list class. What does a linked list class look like from yesterday? How would I make one?
Definite.
All right, what are my parameters?
You would have your
head and next.
Yeah.
All right, head and next. And then what else would I do on head? Self.head equals head. Self.next equals next. Is there anything else that I need to add to this implementation?
Next, default value equals none.
Yes, next equals none, right? And that next equals none basically tells us, hey, have we reached the end or not? So for a reminder, of what a linked list looks like, right? We could have something like LL1 is going to be
Omar, your screen's frozen.
Thank you. All right, is it unfrozen now?
Yep.
Yeah.
Okay, cool. So we could have like an initial node, we could have a head of like 10, and then the next node could be like 20. We can create another node that's going to be, it's going to have the head of this one is going to match up to LL1. And we can basically keep going down the line. In contrast, with a binary trees do not work the same way. So here, let me jot this back down. So we've got 20, and then we could have so we could have LL2 be our head, or LL1 be our head, and then LL3 be the next or something. And yeah, so in contrast to a linked list, let's see, I was missing what's this reference to declaring next as none in the parameters or in the star section? Oh, good question. So when declaring next as none up here, what this means is the default value of next is none. So let's say node 1 is going to be linked list 10. So what I want to do is print out node1.head and print out node1.next. And let me run this. Hello. Perfect. So by setting next equal to none in our def init statement, what I'm saying is I want the default value of self.next to be none. And we see that here. I write linked list, I put 10, and then I don't write anything for next. So it says, okay, if I haven't put in anything in next, then we're just going to set the value of next to none, which it does. But let's say that I now decide, okay, I don't want next to be none. I want next to be like 50. We set that to 50. It's going to say here is, oh, I'm putting in 50 for next. So now I don't need to go back to my default value of none. So I populate next with 50. When we print it out, we see indeed next is equal to 50. But what you're saying is, what if we deleted that from there and just set next equal to none in the self.next? What this does is it says, regardless of whatever value I put in my init function, so regardless of whether I set next in here to 50, if I set it to 300, or I set it to anything, self.next is always going to is always going to be set as none. And we see that here, right? So I put in 10 and then I write down my 50. So I'm like, okay, the next node is definitely 50, right? No, because self.next equals none disregards this value. It always sets none to be self.next. So that's the difference between declaring it in the parameters and setting it to be an instance attribute in the self section.
Hey, Umar, I might be confused, but I'm pretty sure yesterday we were taught that we need to create a different class called node to create each node instance, and then we pass just head into the linked list class, and they're two separate things. Is there a difference between what you're doing now and that method that we were taught yesterday?
Basically what he's calling the linked list class is what I call the node class. It doesn't really matter. You can make a linked list class and then say, okay, well, you have this thing called head and that holds a node. In this case, I mean, in my mind, this makes a little less sense. I would call, I don't know, given what you have here, Umar, how do you add a third thing? As in, the first thing is the head, the second thing is next. What's the third thing?
What do you mean by adding on a third thing?
As in, this is a linked list, so I should be able to add 1, 2, 3, 4, 5, as many things as I want. I see here how you have a head which equals 10 and a next which equals 50, but that doesn't really make sense.
That was just an example for this. So what we would actually want to do is add in a new linked list node, right. Or I guess node is probably a better name for it. So yeah, but it's basically just a collection of nodes that, again, you start off by setting, like, the head here is going to be 10, then the next one, I guess you could even call it, instead of head, like, value, and then start off with 10 and then with 20 and then just keep going down the line.
Yeah, so all he was mentioning is that basically I had it like node, instead of where you have head, I call that value. And then I made a separate class called linked list, which holds a head. You just pass it. Yeah, but you don't, as you can see, you don't really have to have this separate linked list class. If you're making it very simply, you just have nodes pointing to nodes pointing to nodes. And that is a linked list. It just kind of makes sense if you want to start adding specific methods that work on a linked list that don't necessarily work on a single node, then it might make sense to have a class for it.
That makes a lot more sense. Thank you.
Yeah, so like Benjamin was saying, right now in the setup that we have with the node class, for example, we don't have a way to remove a node from the linked list or to similarly append one to the list. So that's where doing something like creating that linked list class that you guys used yesterday that has a collection of nodes in it would make the most sense. But in terms of like just a really, really simple application of linked lists, this is like your very basic linked list node application. So in contrast to linked lists, or I guess well, similarly to linked lists, let's create a binary, I'll call it BT node. It will also have a head and next. I guess we can call them head. Well, here, let's change it from head to, let's call this value instead. I'll change this one to value as well, just to keep the notation consistent. But so remember that what we talked about, I don't remember, I think I deleted the annotation, but here, let me just do it on here. So remember that your linked list is a one-dimensional thing, right? So you've got, it always points to a singular next. So if you have your value and then it points to the next, you have your value and it points to the next node. You have your value and it points to the next node, and so on. But for the trees, you have your node, but that points to a left node, or left node and a right node. And then those in turn point to a left node and a right node. And like so. So whereas binary trees, unlike linked lists, don't just have a singular next value. Instead, what we have is a left and a right value. So instead of next, we have left and then right. So that's the crucial difference between binary trees and one of the crucial differences between binary trees and linked lists. So another thing to keep in mind is, here, let me erase some of these scribbles. So a linked list has it can only stop at one point, right? So your linked list, you have your head, you have a bunch of nodes in the middle, and then you have your end tail node. But with the binary tree, and you've got your root node here, and you've got, let's say, some branches, and I can stop one subtree can stop at a leaf, but my other subtree can keep on going, like so. So you can technically have multiple endpoints for your tree, or multiple leaves. Whereas for a linked list, you can only have one leaf because, again, it's a one-dimensional construct, which goes back to some of the things we were talking about earlier regarding traversal. So if we wanted to create a binary tree, let's say we could do something like tree one. And here, let's change from BT now. Let's just call this binary tree in keeping with the notation used in the slides. So we need to first create a central value. Let's do 98. And now for left and right, we need to create subtrees. So we can create another binary tree for our left and another binary tree for our right. Now for the left subtree for our binary tree, we could create, let's say, 65, and then we could leave that left and right as both none, meaning that that's a leaf, so it stops. And then for the right-hand one, we could create a new tree that has a value of like 104, and then that one also will have a left tree. Let's say that one has like a value of 13, and then, or I guess, yeah, let's say 100, and then a right tree of a value of, I don't know, let's say like 108. So what does this tree that I just wrote out in code look like? So we start off with our initial node, which is 98. That was huge. Let's use text, that'll probably be easier. So I start off with my initial node of 98. Now, okay, I've got my node 98. Now, what's my left and my right? So on the left, I have a new node of 65. So I'm going to draw a little arrow to that. And the 65 one, it doesn't have a left or a right branch. So we just stop it there. So 65 is a leaf. Now, on the right side, I'm going to have another node of 104. And 104 in turn has two left and rights as well. So on the left, we have 100, and on the right, we have 180. So this is the way that we can construct a binary tree in Python and write it out. Are there any questions about how we go from, or how I made the class, one, and two, how it transports from Python notation into a drawn out binary?
So
Yes. I'm sorry, I didn't mean to cut you off. Go ahead, Nick.
Oh, so like say you want to take those leaf nodes 100 and 180, and say you want those to be branches, I suppose, from 65. How would that look in code? Would you just put those two in between, like after 65 on lines 74 and 75, and then binary tree 104 would be down on 76?
So just to make sure I understand what you're saying. So where's my annotate? So you're saying you want the 100 and 180 to also be linked to 65 like this?
Not also, but like just on 65. So if 180 and are only on 65, the left branch, like how would that look?
Okay, gotcha. So remember, so binary tree 65 here is what instantiates our 65 node. So we now need to give 65 a left node and a right node. So to create that left node for 65, well, I just write binary tree, and then our left node for that, we're going to set it to 100, and that's not going to have any further left or right branches. And then if you want to move the 180 over to be the right node, or from on the right branch from 65, then we would say binary tree 180, like so. And then what this would essentially do, again, is we've got our 65 there. It would say, okay, I've got my 65 as my central node. I'm going to move down here. I know that I'm going to create a left branch that goes to a node with a value of 100, and a right branch that goes to a value of 180.
Okay, cool. Yeah, I just wanted to kind of visualize it in VS Code, like in actual code, to make sure I was tracking.
Yep. And again, if it helps you guys, feel free to write this stuff down on your own using pencil and paper or Excalibur or something too, because that's the way I first learned about trees was quite literally by hand drawing them and connecting that to whatever I was writing in code. I think I heard somebody else had a question as well.
Yeah. Say on 65, if you wanted to branch out to the right and only the right and not the left, would you just put binary tree for left as none? And then after that, put the right one?
Yes. So let's say again, let's say you didn't want to have like the 100, you just wanted to have this 180, right? Well, then all we would need to say is, and going back up here, we have a value for value, we have left and we have right. If I set left to none, that means, hey, I'm not going to have a branch going left. I'm only going to have a branch going right. So that basically makes it do this little zigzag there.
Awesome. Thank you.
Let's see. Can you append nodes to the leaf nodes? Yes, you can do that. Not in the current art structure that I have it set up for now. But what you could do is make something sort of like Benjamin did yesterday with that linked list class on top of the node class, and then write functions to append nodes or remove nodes. But that goes a little bit further than what we're going to be talking about today. So today, the main focus is going to be on applying recursion to binary trees and searching for them. But you can append nodes, you can remove them. in trees that are non-binary, you can connect individual nodes to multiple other nodes. It can get a lot more complicated, but for right now, we aren't going to be doing that.
Sorry, I had another question. Just because you mentioned it, now I'm kind of curious. So if that 100 node that is the left branch of 104, so you said earlier like what it would look like if that 100 node was connected to both 65 and 104 above it. So how would that look in actual code?
So that is not something we can do using this current class of binary tree that I have right now. That would be a more complicated implementation. For that, what I would do is I would create a separate node class. Actually, let me write that right now. So you can say like I have like a specific node class. Again, this goes a little bit beyond what we're talking about. And we could do like a def init, and then this would have your self, it would have your value. But I would also create a list of connected nodes. And I'd leave that initially as blank. And then again, you do self.value is value, and self.connected nodes is this. So if I were to create something like this for this class, what I would do is say something like, so you could say like node 1 is like your 98 node, and then you could update the list of connected nodes to add in 65 and 104. And then when defining your node for 100, you could say like node 100 is going to be a new node with the value of 100, and then it's going to be connected to both the nodes of 65 and the node of 104. And then similarly, if you create the 65 node, that would be a node with value of 65, and that's connected to the node of 98 and the node of 100. And then we would do the same thing for the node for 104. So this implementation, as I wrote it down right now, would not work because there's more complicated things that I would need to add in the backend. But like the very rough structure, if you were to have a tree that has nodes that can connect to multiple nodes, this is sort of how it would work.
Okay, sorry, I didn't mean to get into the weeds and all that. And
Oh, no, you're good. Going into the weeds is fun.
And I'm guessing that class node with the connected nodes, I'm guessing that would have to be an inherited class from the original node class, or no?
Nope, I'm just making a brand new class for this one. Yeah, did I name them the same thing? I don't think I did, but yeah, this would just be like a brand new class. But also the implementation of how you do connect nodes to other nodes differs depending on the type of tree. So there's not just one standard way to do it. So binary trees don't have that capability. Other types of trees and networks do. So if you look at something like a neural network is a great example for something like in machine learning. So for a neural network, let me erase here. You have like let's say one input node. Usually it's a fixed a certain number of input nodes. And then those all go to like multiple layers of other nodes. But then those layers of nodes are not just connected like one by one. They also connect across each other like so, and they do weird things with each other when they're connected. And then they all come back together to a singular output layer. So obviously this looks like a mess and not something that you can evaluate using a binary tree. But also there are a lot of different rules that govern how the different nodes interact with each other, et cetera. So to get us back out of the weeds that I'm very clearly going into here, depending on the type of node structure or tree that you're using, which most of the time is going to be something that's commercially available or that you import, they'll have different rules in the class that talk about how those nodes can interact. So like, for example, in this node class that I've defined here, you can technically connect one node to an infinite number of other nodes. In the binary tree one, you can only connect a node to a left and a right. All right, back to the chat. So can some nodes only have single one branch? So yes, they can. And as Eric said, you just have to assign one of the branches to none. So if you take a look at what we did on line 74 here, let me write that down real quick. So I've got my 98 on top, then I've got 65 over here, and the 65 does not have a left branch, but it does have a right branch. So it's still a binary tree, but we're just missing one of the branches because we set it to none. Practical applications. Yes, so as Eric and Benjamin said, searching is the main application of binary trees. That's what we're going to do in about a couple minutes. And yes, as Benjamin said, file systems are trees, which is kind of fun. So and if you've got, let's say take your desktop, for example, right? So you've got let's say it's D. Then you have a series of folders in here that all have things in them. I'm going to try my best to draw a folder using my mouse. That is not a good folder, but that's fine. And then you also have things that are like your executable files. And now inside of your folder, you can have more subfolders and more subfolders and so on. And hey, that looks a lot like a tree. So binary trees are a really simple example of trees in programming, but they're a very good introduction to those sort of tree-like structures with roots and leaves and branches, etc. So I'm going to delete this node class for now because the main ones we want to talk about are linked list and binary tree. But do you guys have any questions about how binary trees work or how the class is created?
So sorry, this is a stupid question. If you were to traverse through the tree and you were, let's say, on a specific branch to create a leaf on another branch opposite side of the tree, you would have to traverse right back up and then back down to that side.
Pretty much, yeah. So again, I'm just going to draw out like a simple example here. Let's do like this and that. So let's say that, by some miracle, you've ended up at this node, but your program needs to create a brand new leaf for this guy. So you can't just teleport from here and just go whoop all the way there. Instead, what you're going to have to do, just like sort of like in a linked list, is you have to traverse back up to your root node and then go from your root node to that other node. And then once you're there, you can do whatever you need to.
Okay, but you can't like set a midpoint or something like another reference point to start from again, kind of like in a linked list. Correct.
No, so with a tree, basically every time that you run a program with a tree, it's almost always, and I put this with the almost caveat, going to start from the root. It'll either start from the root, or sometimes you're going to have it start from a specific leaf, or a number of leaves. And this will get into more detail with searching algorithms, like the difference between depth first and breadth first searches. But we'll talk about those a little bit later in the presentation. But mostly you will rarely, if ever, start from a branch. That's just like kind of wrong. Any other question? Okay, cool. Gonna zoom not, so let me go ahead and pull up my presentation again. Where did it go? And here, let me close out of the annotation and we'll do a new share. Alrighty. hopefully it has frozen and everyone can see it. So this just goes back to what we were talking about with the binary tree class. So again, you've got your value, you've got a left branch and a right branch. And all of those are just connecting your nodes together. So if you look at the example that they have here of my tree, right, you've got your root node of 56, and then your left branch is going to start with, your left branch has a root node of 22 and then leaves of 10 and 30. And your right branch has a root node of 81 and then leaves attached to it are 72 and 90. So so remember, trees are always made of subtrees, which are made of more subtrees, and it's subtrees all the way down until you hit leaves. So something to keep in mind about binary search trees, which is a little bit different from regular binary trees, is that the value in your left node is smaller than the value of the parent, and the value of the right node is greater than that of the parent. So what do I mean by that? Well, let's take a look at these three nodes down here. So 10 is less than 22, and 22 is less than 30. Similarly, 22 is less than 56, and then 56 is going to be bigger than 81. Or 56 is less than 81, so 81 is bigger than it. Then 92 is bigger than 81, and 77 is less than 81. So hopefully we're starting to see a little bit of a pattern here. And basically all of the left nodes are going to be less, or if you have a specific node, all the node on its left is going to be less than the node on its right. And this applies, as it says at the bottom, across all children of a given node. So this is super useful for us if we're trying to search a tree. So if we go back to this tree here, how can we search it to find a specific value? So let's say that I tell you, all right, tell me where 77 is in this tree. How can I find 77? Well, we can start at the root node and compare 77 to 56. Is 77 bigger than 56 or smaller than 56? Well, 77 is bigger than 56. And remember, everything on the right branch is bigger than the value of the node. So we know that we need to look at the right tree. So let me erase that and put in 77 here. So now we only want to look at the right subtree of our big tree, which is all these guys. And what's the root node of this? 81. Well, is 81 bigger than, or is 77 bigger than 81? Or is it less than 81? 77 is less than 81. So we go to the left subtree and look at that. The left subtree is a leaf and it's 77. So we can try this again for another number. Let's say that we want to do it for 10. So we start off at, when we put in 10, we compare 10 to our root node. Is 10 bigger than or smaller than 56? 10 is smaller than 56. So we're going to go take the left subtree. We compare it to 22, which is our next root node, or which is the root node for the left subtree. Is 10 bigger than 22 or is it smaller than 22? It's smaller than 22. So we go left again and we take the left subtree of that node and look at that. The left subtree of that node is the leaf, which has a value of 10. So this is the basic mechanism under which binary search operates. Chris, you could use a while loop to traverse it, but I don't know if I'd honestly recommend it in this case. Because again, remember that the best use case for recursion is when you're repeating the same function call every time. And in this case, that's pretty much what we're doing, right? So as it says here, like for this use case of something that starts down with 4, and you're trying to find the number 7, right? you guess down the middle, 7 is bigger, so you want to look at the right subtree, but we're looking at a tree again. So we're basically going back to that same search function. So because we're always looking at a tree, and we're performing the same operations on a tree, regardless of what that tree is, and that tree is based off of the tree we were just looking at, it's better to use recursion. Sort of like with factorial and Fibonacci.
What if you can find a target value?
If you can't find the target value, that's something that you are going to be doing in one of your assignments. So no hints.
So do you always compare the target value to the root node? That's what it seems like. That's the pattern, right?
Yes. And here's the reason for that, right? So remember that the characteristic of our binary search tree is with respect to the root node, everything to the left of it is going to be less than that root node. And everything to the right of it is going to be greater than the root node. So when comparing, it only makes logical sense to compare everything to the root node. Because based off of this root node, you can tell, okay, I need to look at the right subtree or the left subtree. And if I need to look at the right subtree, then I just do the same thing again. I compare everything to the root node of that subtree. And I say, is it less than or is it greater than? And if it's greater than, then I look at the right subtree. And if it's less than, I look at the left subtree. And basically, by comparing to the root, we get access to the subtrees, which is what's helpful. Nicholas, quality where left branches or lesser values. So this is a characteristic of all or almost all binary search trees. I've definitely dealt with problems before where you have a binary, where you need to create a binary tree from they give you a list of numbers and then they tell you, okay, create a tree based off of this list. There are also problems that you can encounter where they give you a binary tree whose nodes are all in a messed up order and you have to sort them out properly. But in general, binary trees are supposed to be set up this way. So they're supposed to be set up so that the nodes on the left are lower, the nodes on the right have a higher value.
So if it's not,
go ahead.
It's wrong.
How do you mean?
So if it's not sorted out in this manner, that binary search tree is built wrong, or it's not a binary search tree. Is that what you're saying?
Yeah, pretty much.
Okay.
So for all examples that you encounter that use binary search trees, basically assume that they fit this format unless somebody tells you otherwise. And if somebody tells you otherwise, it's a binary search tree that's been modified. Okay, so yeah, back to this example, right? You've got a tree with the numbers 1 through 8 on it, and you're trying to find where's the location of 7. Or basically, we're playing the higher lower game. So you check, all right, 4. Is 4 bigger than my number or smaller than my number? And we say that we need to go higher. So if you need to go higher, you go to the right. So you go to the right tree, you guess 6. And for 6, we have to check, is it higher than 6 or lower than 6? Make sure that it's higher than 6. So then we look at the right subtree, which is 8 and 7. And we check, is it higher than 8 or lower than 8? And it's lower than 8. So then the only option is 7. So now we're going to talk very brief. Well, I guess before we talk about complexity, does searching through a binary tree make sense? Does the way that I'm talking through this make logical sense? Or does anybody have questions?
Makes sense to me.
All right. So let's keep moving forward. So this is something we're going to talk about more tomorrow, but we're going to discuss a little bit of complexity. So binary search is a search algorithm. And whenever we have an algorithm, algorithms have something called time complexity. which depends on the input size. So an O log n time complexity basically means that as the number of inputs or a number of nodes in my algorithm gets bigger, the time it takes to run will scale relative to the logarithm of the number of inputs. So for example, here they use log base 2. So if I give you 8 nodes, for example, you only need to make a maximum of 3 guesses to guarantee our answer. And we can see that here, for example. So the most number of guesses that we're going to need to get 7 is indeed 3, right? Because that's the furthest node down that we're going to ever need to look at. Why is it 3? Well, you've got how many subtrees? You've got 1 subtree on the left and 1 on the right. And then on the right, you've got 1 more subtree, which is the subtree of 8. And then you're there. So a very brief summary of time complexity and big O notation. But you guys are gonna talk about this a lot more tomorrow, and I don't want to spoil that lecture. But basically, this complexity of O log n for binary search is something that's going to hold true for any number of inputs that we have. So if we have, let's say, 16 inputs or a 16 node tree, the maximum number of guesses that we're going to have that we're going to need to use is 4. Or for 32, it's going to be 5, and so on and so forth. So for us right now, complexity or time complexity will basically tell us the number of guesses that we need in order to guess or search for the number in our binary tree. So important notes for interviews, because this is going to come up. Time complexity is something they love to talk about in interviews, which is, again, why we're spending a lot of time on it tomorrow. So O log n is the only complexity case worse than constant. So what on earth do I mean by a constant time complexity? So let me try drawing a graph here real quick. So a constant, so we have O and n. So a constant time complexity basically means that regardless of how many inputs my function I get, whether it's 1 node or like 3 bajillion nodes, the program is going to take the same amount of time to run, which sounds great. Next, we have O of n, which is linear. So it says as the number of inputs increases, the time to run increases by linearly or proportional to the number of inputs. And then log n, if I remember right, looks something that sort of goes underneath of linear, but worse than O of 1. Here, let me redraw this. So this is O of n, this is O of 1, and O of log n is a kind of looks something like that. Kind of. I mean, not exact by any means, but you'll see far better diagrams of this tomorrow. But these are 3 things I would personally write these down for your interviews, and just keep them in mind, because you will be quizzed on this stuff. The second thing to keep in mind is binary search is the only searching algorithm and the only algorithm that is guaranteed to be O of log n. There are proofs of why this is so. We are not going to go into those today because that's honestly a bit too deep for what today's class is designed for. And lastly, if the input is going to be pre-sorted, so remember looking at this tree, where did we go? There we go, this slide. All the nodes on the left are less than all the nodes on the right. Your tree comes in pre-sorted for binary search. So if your input or if your tree that you're getting is pre-sorted like this, use binary trees and use binary search to sort whatever it is that you have to search. And that's at the bottom. One of your homework assignments is going to be to do a problem from yesterday, but you're going to get a sorted array instead of unsorted, and that's going to help you cut down the search space every iteration. So keep your indices in mind for that. So as it says here, traversing a tree needs to be done recursively, given the nature of the structure, which is, again, what we talked about. So let me go ahead and pull up my VS Code real quick. Where did my VS Code go? Oh. There we go. Okay. So let me pop in the binary tree. And we'll also pop in the search algorithm. And where's my screen share? Wrong tab. No. Okay, where did it go? Oh, there it was hidden. Okay, let's do new share and VS Code. All right, so I'm guessing everybody can now see my VS Code. And Ethan, this is literally the last thing that we're talking about today. So it'll be like 5 to 10 minutes, and then you'll get lunch break. So can you guys see my VS Code? Okay, cool. So let me go ahead and delete that. And let's talk a little bit. So this is just the code from the lecture slides that I just copy paste into VS Code because it looks a lot nicer than GitHub. So they create a binary tree class, which is exactly what we made with our init, right? You've got your central value, you've got your left tree, and your left subtree and your right subtree. Then they just create a string function that's going to print out your binary tree. We don't need to talk about it in too much detail, but basically it will recursively go through your tree in order to print out your tree. Example of a binary tree, we already went through this, but you've got your root node, you've got your left subtree, and you've got your right subtree over there. And then for binary search, remember what we have to do, right? We need to split our tree down the middle, check if the value we're looking for is our root node. If it's not a root node, is it bigger than the root node, or is it smaller than the root node? If it's bigger than the root node, or if it's smaller than the root node, we need to check the left part of our tree. And if it's bigger than the root node, we need to check the right part of our tree. And basically just keep running this until either if tree equals none basically means is the value not found? Like, have we run through the entire tree? If it is, then we're done. If the value is equal to the value of the node, hey, we found our value, so return that. That's basically how binary search works. It's summarized really, really quickly. Now, I know that all of you guys probably want a break, and trust me, we're done with the lecture material for today, but do you guys have any questions about binary search? Like how the search algorithm works in this specific case, how the binary tree works, anything like that?
Just a quick question not related to this. Can you use recursion for like a sorted array, like the same way like we just used this?
Yes, and that is something that we're not going to look at just right now, but if you want to, I would look at sorting using something called bubble sort, which is basically a recursive method for sorting an array. And that's a really common interview problem and also use case of recursion.
Thank you.
Can I run the binary search function? Sure. The only thing, it's not really going to tell you too much though. But we can walk through it. So let me change this from looking for 1 to looking for, let's say, the value 10, and run that.
I guess my question for this is like, when you run it, like, normally would you have a list that's being passed into this, a sorted array? and you would pass
No,
this?
so this one is the binary search function, as we said here, it takes in a tree. So it'll take in like this my tree thing that we created, or that Benjamin created in the problem. It'll take in again binary tree, which is just your binary tree object. So if you got like a sorted array, you'd have to first convert that array into a tree and then run that into your binary search algorithm. Or if you already had a sorted array, you could rewrite your binary search function to forget the tree part and only run it on the array, but that's a bit more complicated.
Okay, yeah, that makes sense. I just wasn't sure exactly what the standard is like that you're given, but that makes sense how you have to make it into a tree.
Yep. So whenever you do a binary search algorithm, you basically always have to turn it into a tree.
I have another question. So here in the binary search function we have, you're basically moving down every node, either going left or right recursively. Yes. Earlier we were talking about in a situation where you would have to go back up the tree and then go down a different side. How would you actually do that? Other than like here we're going down towards all the leaves, but how would you go the opposite way?
So if you were going to go the opposite way, for that, I would have to give you a starting node. So you will encounter problems like this. They're a bit more advanced than what we're talking about right now. But to briefly summarize, if there are some problems, for example, that say, how many nodes do I have to go through to get from one node on the tree to another node on the tree? So for a problem like that, what you would do is you'd first have to go from your first node up to the root, and then go from the root down to the other node, essentially. So for that, what you would do is you'd say, okay, let's start from my first node and figure out where I am on the tree. Once you figure out where you are on the tree by using your less than and greater thans, then you can start traversing. And then after that, it basically turns into a little bit of a binary search. So I know that was a little bit of a nebulous explanation, but it's a little bit more complicated than I think we have time to talk about today. But I would encourage you to look at, I would encourage you, though, if you're interested, to look up traversing binary trees, or like distance minimization, because those are basically the two keywords that are used whenever people talk about running through trees like that.
So basically, the way this function is set up right now, you couldn't just write something within this function and go back up the tree. Like you would have to either rewrite it or like set it up in a different way.
Exactly. Because right now, all this does is it says, all right, split the tree down the middle. Am I going left or right? Okay, split it again. Am I going left or right? Split it again. Am I going left or right? And it always moves downwards and in one of those directions. If you wanted to move back up the tree, then things get more complicated.
Okay, thanks.
Yep. Any other questions about either binary search trees, recursion, binary search?
Hey, Umar. Oh,
yeah.
Never mind.
Oh, no, you're good. What's up?
I was just gonna ask you if you could scroll up and then just like zoom out just a little bit, just so I could see the tree structure. Yeah, thank you.
Sure. Yep. So also this is taken directly from the second to last slide in tonight's in the lecture. So if you go to the code examples page for today, which I'll paste into Slack as well. Where's the inform?
Are we supposed to write it like that, or how we did it the first time?
It's basically the same thing. So the way that I wrote it is a little bit more spaced out. You don't have to write it the way that I did. I think that this one just has less indents, which probably just looks better. I've also seen people write their binary trees all in one line like this, which is really ugly. I would highly recommend not doing that just for ease of like comprehension and understanding. But you can write them however you want to, as long as you're making it obvious that there are separate branches. And I think this one does that pretty well. I think the one I did does it pretty well as well. Eric, to answer your question, yes. So this is it's an O of log n algorithm. And because it's a binary tree, it's going to be log base 2 of n elements to find it in the worst case. So if there's 8 nodes, you should take at most log 2 of 8, which is 3 tries or 3 run-throughs to find it. If there's 16 nodes, it should be 4. Anything else? Okay, well, if not, I think you guys can break for lunch. Again, let me know if you guys have questions. Just checking the schedule for the rest of the day. It looks like after this, you guys have teamwork time, and I don't see any guest speakers on the list, so feel free to. Oh, another hour. Oh, you know what? Actually, you might be right. It might be another hour till lunch on the schedule, but we don't have material for another hour, so we're doing lunch now.